See, what are the properties of amines? See, amines are usually fishy order, and aryl and aniline are usually colorless but get colored due to the oxidation. So when it gets oxidized, it will get a nitrosoform, and nitrosoform is usually colored, which is yellow color usually. Okay. Lower alkyl amines are soluble in water. That includes methylamine or ethylamine. And as you go towards the higher amines, 4 carbons or 5 carbons, it is not soluble. Okay. Next, if you notice 1 degree and 2 degree amines, they usually have intermolecular hydrogen bonding. Got it? So, for instance, if you have nitrogen with 2 hydrogens here and CH3 here, this is primary amine. So, here you can have hydrogen bonding with the next nitrogen possible, like this, CH3. Same goes here and same goes here. So, like that, primary amines, each of them will have respective intermolecular hydrogen bonding within them. And that leads to have a higher boiling point as well. Okay. While 3 degree, while 3 degree has no hydrogens, so its boiling point is lowest. So the order will be 1 degree, 2 degree, and 3 degree amines. Okay. Usually, what you would notice is that if you compare alcohols, amines, right, and alkanes, usually alcohols will have a much stronger hydrogen bonding. So, if you have a comparable molar mass, alcohols will have higher boiling point than amines, primary amine. Then, within primary amine, if you have more branches, then the boiling point decreases. So you can see then comes secondary amine, then comes tertiary amine, and the last comes alkanes. Clear? Now, if you have to add it across the functional groups, just for the sake of remembering once, remember this part. If you have a comparable molar masses, carboxylic acids will definitely be the first one, and then comes alcohols, and then comes primary amines, and then comes ketones, and then comes aldehydes. Okay, and thereafter comes alkyl halides. Correct. uh, then comes ethers. Okay, after ethers, this is where you will have alkanes. Got it? So across functional groups, if you have to compare, then this is typical order of boiling point of comparable molar masses. Physical characteristics wise, these are the few factors you need to know from amines. Now, when it comes to chemical reactions of amines, first let us see how they act like a base. So when they are acting like a base, we expect them to react with acids and convert into salts. And that's typically observed that if you have any primary amine react with HX, it will give you ammonium salt. Now, it would happen even with an alkyl group or an aryl group. But interesting part here is this salt is soluble in water, while these amines are generally insoluble in water. So you could see how the property of solubility changed as soon as you add it with some small amount of acid. Okay. And that's what we'll take it as an advantage specifically to separate the organic compounds. See, amine salts react with NaOH and can be regenerated to the parent amine. That is, once you get this salt here, you react that with NaOH again. The OH minus will take away H plus, and that will give away, RNH2, H2O, and NX. Now, what happens here is this amine is not very soluble in water and this salt. So, these two will get dissolved and this will come out. Okay. Come out as in it will be in a liquid state, but usually have a lower density. So, it will float up. This is what will take it as an advantage. Check out. if at all I am supposed to do separation of two organic compounds like toluene and aniline, let's say, okay, between toluene and aniline, if you compare, when you add aqueous HCl here, you'll get ammonium chloride first, okay, anilinium chloride first, because, and this will get dissolved in water while nothing happens to the toluene. So what I'm doing now, I'm taking a test tube which contains half composition of water and half composition of ethers. So as you add these two to the solution, you will notice that this salt will get dissolved in the aqueous form and this toluene will get dissolved in the ether form. So this is an ethereal layer. Okay. And now by fractional distillation, we should be able to separate the ether from aqueous solution. So that way these two solutions got separated. Okay. And once they got separated here, this which had anilinium ion, when you add it to NaOH and further add ether into it, so now aniline will form and that aniline will get dissolved in ether and aqueous solution will be left with simple salts. So this way we are able to separate out toluene as well as aniline. Clear, girls? So I hope you guys understood how it works.
Yes.
Right. With the second reaction, which is acylation. Acylation is when you have an amines reacting with acid chlorides or anhydrides, giving a C double bond O R substitution. Okay. Typically, the lone pair from nitrogen will attack here. First, it will release out this Cl minus, and the released Cl minus will take away proton and convert into HCl. Okay. So you would get an amide form, N substituted amide form, and an HCl form here. But obviously the HCl is an acidic medium, so this reaction can further take place and go back to the reactant. So if at all our objective is to stop the backward reaction here, okay, so instead of using just in any solvent, you better use in pyridine. When you use it in pyridine, the pyridine will take away that HCl and convert into pyridinium chloride, thus avoiding the backward reaction. Sorry. This is typically how the acylation works. Okay. The third reaction is bromination. Bromination of amines, usually we do it for anilines. So when you take anilines, the lone pair from nitrogen can attack on bromine. Now this could be directly attacking or this could be attacking on ortho para positions. That depends upon the solvent exactly. If you are taking CS2, that is non-polar solvent, you know that NH2 is a very, very strongly donating group. So it will activate the benzene ring very strongly and activate specifically at ortho and para positions. So from this ortho position, it can attack on bromine, and because it is highly activated form, it can attack simultaneously. I mean, it can happen first on this ortho, then on this para, then on this ortho. So like this, it can happen on all three positions, right? Now, if you take water instead of CS2, that will be even more, faster. Reason being, bromine in water will try to become HOBr, which will have delta positive and delta negative plus HBr. So this would bring a lot of bromine positive charge, Br plus, which is an electrophilic part. So the attack would happen even more easier if it is aqueous solution present. And here also you will see a white PPT forming. Okay. Well, so I hope it's clear. Right. Just give me a second. When it comes to bromination, it will happen at all three positions, 2, 4, 6 position. But how do we need to control this bromination so that it can only happen at one position, either at ortho or para? In that case, what you do first acylation step. that is, you take aniline, react with acid chloride, you will get an acyl formation here. Okay. Now, this NHC double bond of CH3 is a moderately activating group. Reason being, the lone pair is involved in resonance on both sides, towards the benzene side also and towards C double bond O also. That's why now the ortho and para are not as heavily activated as earlier. Hence, if you do bromination, typically you might get a minor product on ortho and major product on para. So let's say this is a major product. So with one bromine at the para position. Thereafter, if you treat with NaOH, again the acylation will go away, acyl part will go away, and this NH will become NH2. And that's how you will get this as, NH2 with a Br group. So you can notice this. Amines react with the benzoyl chloride also in a similar way, and this reaction type is called as benzoylization or benzolation. Okay. Instead of CH3, if you have C6H5, this is called benzolation. Clear? Now, let's see the other reaction. This is used as a test for primary amines also. This is a typical test for primary amines known as carbyl amine test. So what we do in carbyl amine test, see, we take any primary amine. It could be alkyl or aryl, it doesn't matter. You react with chloroform in the presence of NaOH or KOH. Okay. So what it does is OH minus will take away H plus. Okay. Generate CCl3, this one, CCl3 minus. CCl3 minus is unstable because all chlorines will repel each other because they are on the same plane. And they depart one of the chlorine and convert itself into an intermediate carbene. Carbene has a lack of electrons. It has an empty orbital to which the lone pair of nitrogen can attack as a nucleophile. As it attacks, you will see this carbon gains negative charge. So internally it will take away H plus, giving this, carbene substituted amine. Thereafter, because chlorines are good leaving group, the lone pair from the nitrogen's end will push it to remove this chlorine out. So one chlorine is out. Again, nitrogen got positive charge, which means this hydrogen will have sufficient positive charge on it. So basic group will extract H plus, gets a lone pair. Again, the lone pair will push to remove the second chlorine. And now carbon has one hydrogen here. So OH minus can take H plus from carbon, and that's how you can get isocyanate. See, isocyanate is a very foul smelling gas or foul smelling vapors. And once you get that foul smelling vapors out of test tube, it gives the confirmation that what we are doing is for primary amine. Okay. It is no compulsory that this has to be only alkyl or aryl primary amine. Any kind of amines, any kind of primary amines. You can see this primary amine, or you can see this open primary amine like this, or you can use this primary amine, or you can use benzyl primary amines, or you can use simply CH3 NH2. All give positive bicarbonate, positive carbylamine test. Okay, so this is carbylamine test. Clear? Any doubt in this? Mind you, carbylamine test is always going to be asked in exam in one form or the other. It could be a direct question, or it could be somewhere linked inside somewhere in the question. Okay, so keep in mind what is carbylamine test. The next official test which differentiates 1 degree, 2 degree, 3 degree amines is Hinsberg test. This is called Hinsberg test. So what we do in Hinsberg test is we take one reagent, that is either it has to be benzene sulfonyl chloride or it has to be toluene sulfonyl chloride. Toluene sulfonyl chloride is also called as tosyl chloride. We usually write it as TSCl. Okay. Now what exactly happens here? See, if I take 1 degree amine, react with TSCl, okay, from 1 degree amine, this is what you will get. So RNH2, so this H from here and Cl from here, that is from tosyl chloride. These two will come out as HCl and nitrogen will get added onto sulfur. And this is a compound form, right? So this is sulfamide, known as sulfamide. So N substituted sulfamide. This N substituted sulfamide, what you would see when you add a base to it, because it is a white PPT, the minute you add base to it, OH minus will take H plus and convert into a salt form, which dissolves again in aqueous solution. So this will get dissolved in aqueous solution. And if you take this dissolved form, right, if you take this dissolved form, again add it with acid, you will get back to this one. Again, you will get a precipitate, you will get white precipitate. So see the sequence of events, what we are trying to do. First, we have an colorless amine liquid in a test tube. Then we added tosyl chloride onto it. Okay. And immediately you're supposed to get a precipitate. Correct? White PPT. And the minute you add KOH, the white PPT should get dissolved again. It should get dissolved. And again, when you add HCl, it should regain back that white PPT. Okay. So this series shows how 1 degree amine works with tosyl chloride. Now, if it is 2 degree amine, when it comes to 2 degree amine, see, if it is 2 degree amine, it reacts with tosyl chloride first, correct? So convert into a white PPT, just like 1 degree amine. Here also it converts into white PPT. Thereafter, when you add base like OH minus to it, okay, now this OH minus has nothing to extract from here. Earlier there was a hydrogen, but now there is nothing to extract from this amide. Hence, no reaction will take place. That means the precipitate will remain as a precipitate. So whether you add KOH or furthermore whether you add HCl, the precipitate does not change its identity. And this is what happens in 2 degree amine. If it is 3 degree amine, when you react with tosyl chloride, since it does not have any hydrogen to lose right from the start, it would only appear like a salt form which is in a dissolved source. So there is no precipitate forming at any event or any point of time. Okay. So with 3 degree amine, no precipitates are observed. And that itself is an indication that there is a 3 degree amine. Hinsberg test is identification of 1 degree, 2 degree and 3 degree amines. At the same time, it can be used as a separation test. Imagine I have a liquid content of 1 degree, 2 degree, 3 degree amines together. The minute you add tosyl chloride to it, 1 degree and 2 degree will get precipitated. 3 degree will remain as a soluble solution, correct? So you can separate out by filtration. Okay. Then once you get the filtered white color PPT, add KOH to it. The one which get dissolved in it, that has to be 1 degree. And one which does not dissolve, it will remain the same, that has to be 2 degree. Clear, girls? Okay. That's how you can use it for the separation process as well. Right. See the next test. The next test is about HNO2, nitrous acid. How nitrous acid will help us uh, identify 1 degree, 2 degree and 3 degree amines. If it is a primary amine and react with NaNO2 and HCl, NaNO2 and HCl will give you, NO plus, NO plus. And NO plus is an electrophile. So N double bond O is there. The lone pair will attack here. You will get this as Rn2 plus here, disonium salt. And from disonium salt, N2 can be removed out. Okay, N2 can be removed out. And because you keep it in an aqueous solution, the carbocation will be attacked by water and it will convert finally into an alcohol. Okay. In fact, if there is a chance of rearrangement, that will also take place, but eventually you will get an alcohol only. Okay. So if it is a 1 degree amine, what do you notice? Typically, you will notice an N2 gas coming out. Okay. It is inert to fire, so which suggests that it is neither hydrogen or oxygen. So definitely it has to be nitrogen gas. Okay. So if nitrogen gas is released, means it has to be a 1 degree amine. Hmm. Next, 2 degree amine. If it is a 2 degree amine, since you are having an NO plus, the lone pair will attack on NO plus and converts into this N and double bond O. And this N and double bond O, right, is actually a yellow color oily liquid. It is a yellow color pigmentation which comes to the solution. So it is a yellow color oily liquid. Okay, clear, beta? Now, this formation of yellow liquid is what we call it as Lieberman nitroso test. This is what we call it as Lieberman nitroso test. In fact, we discussed about Lieberman nitroso test before. Okay, got it. Lieberman nitroso test before, where we studied is for phenols. Okay, identification of phenols. Clear? We call it as GRB test. First, green, red, blue color formations. Okay. So Lieberman nitroso test is used for two causes. One is to detect phenol. The other one is for secondary amines. Next, if it is a 3 degree amine, and when you react with NO plus, it will again exist like a salt form, a colorless form. Okay. It is not giving any nitrogen gas or anything like this. So it will remain dissolved in the solution. So it is definitely not 2 degree. There is no gas coming, definitely not 1 degree. And that's how you will get a 3 degree amine. Okay. But see, listen, release of a colorless gas or a colorless liquid present, these are not very good confirmations for a particular reaction. Understood? These are not a great confirmation forms for a reaction. That's why nitrous acid typically is used for 2 degree amines only. Okay, for 1 degree and 2 degree, although there is slight differentiation, we can say on paper, it's difficult to visualize or difficult to get it separated on uh, practical purposes. Okay, that's why nitrous acid is specifically used for. Suppose if the question is being given nitrous acid test, that means what do you choose out of the options? You should choose 2 degree amine. Girls, clear? Okay. Next, see, in case if you have a regular primary amine and you react with a nitrous acid, that is NaNO2 in HCl. Okay. In NaNO2 and HCl, what are the reagents which are present? See, water is sufficiently present. Chloride will be formed. Chloride will be present here, and NO2 minus will be present here because it will be Na plus and NO2 minus. So this NO2 minus will be present here as well. Which means when you react this with HNO2 or nitrous acid, you will notice that it will get N2 plus. Okay, that is the diazonium salt formation. And in the case of alkyl group, it is extremely unstable. So N2 gas will come out immediately, creating a carbocation. Okay. And once you get a carbocation, now these reagents can attack like water, chloride, right? Nitro. So we can have NO2 also, nitro group here, and ether also. So basically, one alcohol which is forming can attack, sorry, not this alcohol, this primary alcohol which is forming can again attack back the carbocation which is already existing. So as it attacks, it will lead to the formation of ethers. Like this, you can get ethers. Okay. In fact, just like how it happened, with the carbocation here, correct. This carbocation can be further rearranged also. So that means this positive charge can actually go towards this positive charge and thus gets rearranged as well. Okay. And since it can be rearranged, so we can say that uh, This carbocation can also show all these reactions. So it can get alcohols, it can get chloroalkane, you can get nitroalkane, you can get alkene on heating, you can get these ethers as well. So notice there are so many different products you can get from before and after rearrangement cases. Clear? Major product, because water content is more in here. So the major product always has to be alcohol. Clear? So remember, major product is always alcohol in this case. Okay. Next. So your CH3NH2 in the presence of NaNO2 and HCl. So this NH2 will convert into N2 plus. Okay. And N2 plus will be released. You will get CH3 plus. And that when you react with water becomes alcohol, with chlorine becomes chlorobenzene, with nitro becomes nitrobenzene, and with ethers you'll get this ether form. Okay. And you see the same question, NH2 when you react with NaNO2 and HCl you'll get disonium salt, and disonium salt will easily release out as N2, create a carbocation. The carbocation can also undergo compression. So this was an 4-membered ring. Now this will become a 3-membered ring because 3-membered ring converts into a CPM carbocation. CPM carbocation is very stable form. Okay. So therefore CPM carbocation is formed. Done. Now you know that CPM carbocation also show resonating structure like this, which we call it as dancing resonance. So on a whole, I have this carbocation, and this carbocation existing. So as water attacks them, you can get alcohols of these three kinds. Out of this is a major product, but the percentage is very comparable with the 4-membered ring. Okay. Next is disonium salt formation. You can see uh, here you can see amines, how it can make a disonium salt formation. Let's see that. So you can see this aniline form. When you react with HNO2, it will form disonium salt. Now there is one important point that you need to notice here is that when it comes to disonium salt, right, there are two types of disonium salt. One is alkyl, CH3, let's say N2 plus. This is called alkyl diazonium salt. The other one is aryl. Aryl means directly connected with this N2 plus like this. Here plus I is the only support of methyl which it has. But here if I write the exact structure N triple bond N with plus charge like this, you can see along with this group it can give a double bond character here and make a resonance stabilization like this. Positive charge and then double bond and double bond N. Okay, minus and plus. This is how you can get a disonium salt getting stabilized. So that's why, okay, it is extremely unstable. The first one, extremely unstable. And in fact, even as weak as methyl carbocation, it is a very unstable carbocation, still it will get released. While here, stable carbocation, stable, you know, below 5 degrees Celsius. So this will be stable below 5 degrees Celsius. So as long as if you perform the chemical reactions at a lower temperature, then you can still isolate the disonium salt and make the reactions happen. Okay. So all the disonium salt reactions, benzene disonium salt reactions, they are all happening at below 5 degrees Celsius. Okay, beta. Now if you go beyond 5 degrees Celsius, what would happen? So in here also, if you get a disonium salt and if you are going temperature 5 degrees Celsius, then this will definitely break as well. So you'll get positive charge plus N2 gas. Done. Clear on that? Right. Now notice what type of reactions aniline can perform as a disonium salt. So you can see you have N2 plus and N2 plus when you react with, you know, CuCN, okay, and N2 plus when you react with CuX, where X is bromine or chlorine, then cyanide will replace this uh, position, the N2 position here, and you will get a cyanide form. While here you will get X, which is halogen form. Okay. Now both these reactions together, because they are been using the cuprous salt, it is called as Sandmeyer's reaction. This is called Sandmeyer's reaction. In here, Sandmeyer's reaction, you will see, okay, set mechanism is observed. Set mechanism means single electron transfer. Single electron transfer. And single electron transfer implies that there is a radical formation. So due to that radical formation, you'll get these products. So remember the name. What is this one? Sandmeyer's reaction. So you will get cyanobenzene or you can get halobenzene. You can get the similar reaction even if you take copper dust, add it with X2, correct? And here X being chlorine and bromine. In that case also you will get this X formation. Here it is also similar product, so this is called as Gattermann reaction. And similar problem, this is also an set mechanism. Clear? The name is Gattermann's reaction. Next. If you compare this with uh, BF3 plus HF, okay, so here first you will get is, you know, uh, N2 plus and BF4 minus. We'll get this as BF4 minus, a salt form. And only when you heat it, the fluorine F minus can come out of BF3 and attack here, remove the N2 gas and BF3 vapors. And that's how you can get fluorobenzene. Okay. And this is called, okay, Boltzmann reaction. This is called Boltzmann reaction. These are important name reactions for disonium salt. Remember that. Okay. Now, the other type of reactions include, you know, reaction with H3PO2 followed by hydrolysis. Now, this will lead to the formation of, okay, correct. This will lead to the formation of phenol formation plus H3, sorry, H benzene formation plus H3PO3. So H3PO2 is getting oxidized to get this benzene form. Now this can also be done by ethanol. So that means if you take ethanol, you can get this as CH3CHO. It will get oxidized and this benzene part will get reduced. And similar terms, if you have reaction with only warm water, if you use only warm water, we will get phenol. You can directly get this as phenol because N2 plus will go away. Okay, this will happen just like that because you're heating it, right? The minute you start heating it here, so the reaction will go in this direction. So carbocation will form on that water molecule has been attacked. Okay. Next, if you treat this with phenol, correct, coupling reaction will take place. Coupling reaction as in, if you have phenolic group here, on the para position you can have N double bond N attachment with this benzene group. So this itself will act, this entire group will act like an electrophile and connects on the para position. This will connect on the para position. On a similar view, you will notice one more reaction. Okay. Now this time, right? So this is about aniline formation. So in case if you have aniline here, so instead of OH, now if you have NH2, so you'll get this as NH2 here. The product kind is the same. The reason why this is happening is both OH and NH2 is very, very strongly donating. Clear with the reactions? What are the disonium salt reactions? Please go through it once quickly, then we'll go further. Let me next check out about the reaction which is Hoffman exhaustive elimination. We have done this reaction beforehand. Okay. Exhaustive elimination as in you start pushing a lot of methyl groups towards the nitrogen so that it gets a positive charge. And once it gets a positive charge on it, you can perform an elimination. For example, if you have CH3, CH2, NH2, and then you react with CH3I, the lone pair from nitrogen will attach. So you'll get this as CH3. So you can see there will be 3 CH3 groups here. Got it? And this will have a positive charge on it because extensively methylation has happened. Lone pair has attached here multiple number of times. You'll get this form with I minus as the salt form here, correct? Then when you treat with AgOH, okay, so when you treat with AgOH, so OH minus will take H plus from here, and this entire group NMe thrice will be removed, and that way you can have CH2 double bond CH2, so that will make it alkene plus NMe thrice. Okay, that's how you get an alkene. Now it would usually give an Hoffman product, which means, suppose if you notice this case here, the lone pair from nitrogen attacks one time, the hydrogen will leave. Second time, again the attack would happen, one more methyl will come. So you will get this quaternary ammonium salt. Thereafter, AgOH, which is a base, this base can go extract H plus from here, or it can get extract H plus from this beta position. There are two different beta position. This is secondary position, this is tertiary position. And you know that the procedure happens via formation of a mild carb anion character. And you know that carb anion character is much better at second degree position than third degree position. Hence, OH minus will take away H plus from here, bond will break, and you'll get a double bond here and NMe twice. Clear? And again, suppose I perform the methylation one more time. So I'll get N, B, 3 times methyl group here. And then when you react with OH minus again, this time H plus has to be, because there is only one type of beta position here. So you will have to remove H plus from here and double bond will form here. So that's how you'll get this product. So with first excess reaction, you'll get this product. Again, if I perform the excess product reaction, you'll get this product. Okay. Clear with Hoffman exhaustive elimination. Next, Cope's elimination. See, if you have a 3-degree amine and then you do H2O2 reaction. So that is 3-degree amine oxide will be formed. See, this is the example. This is a 3-degree amine with peroxide. The nitrogen's lone pair here will be attached on oxygen and convert that into O minus. So you'll get this as N plus and O minus. This on heating, right? This O minus will try to extract beta positions hydrogen here or here. Now, which beta carbon is more stable here? This one, because there is a phenyl group which will help it, mildly undergo resonance. So therefore, O minus can extract H plus from here, and that is a product you will have because it will break from here. O minus will take H plus from here, and this is a product of nitrogen, and alkene product will be formed this way. Okay. So this type of elimination is a syn elimination. Syn elimination as in internally within the same side, both nitrogen's removal and hydrogen's removal are on the same side. Okay, with Cope's elimination. Right, next. There is one more test that amines are very specifically used for, known as half-pen mustard oil test. Okay, what you be doing here? So if at all I take 1-degree amine, react with CS2, okay, in the presence of HgCl2 here. So you would notice that we will get, lone pair attacking here on carbon, correct? So we will get this as NC double bond CS, and it is supposed to as SH also here, S minus. So when the lone pair closes here, that S minus will leave and converts into H2 HGS. That's why we take it in the presence of mercury, so that S2 minus can easily leave out and giving us a precipitate, a black color PPT of HGS. Okay, so what we got is, thioisocyanate. This is thioisocyanate. And thioisocyanate, this particular product which is formed, that has a smell very similar to that of mustard seeds. Okay. So if at all we get this mustard seed smell, so we say it has, you know, we say that it has 1-degree amine. So 1-degree amines must be present. Clear, beta? This is the other test. Next one is azo dye test. Azo dye test, just now I showed you as a reaction of benzene disonium salt. That is when you take aniline, react with N2 plus. From the para position, it will connect to nitrogen, and that's how you will get azo dye color, which is yellow. And these three colors you could remember. Beta naphthol will give you red color, phenol will give you orange color, and aniline will give you yellow color. Okay. So this is a yellow color dye. This is beta naphthol, which will give red color. This is phenol, which will give you orange color. Right? See, what are the general compounds of aniline derivatives? See, one is this aniline. Then, if at all you make an acetyl group on it, it is called acetanilide. If it is benzene, you call it as benzanilide. If NH2 and SO3H, both of them are present, then you call it as sulfonalic acid. Sulfonalic acid. Usually, sulfonalic acid exists always as, because internally you have a base, internally you have an acid. So the base can take H plus from here internally and convert into NH3 plus and SO3 minus. So instead of existing in this form, sulfonalic acid usually exists in this form, and this form is called Zwitter ion. If a molecule internally has positive charge and negative charge together existing, okay, like an ionic compound, then that is called as Zwitter ion. So this aniline form will have Zwitter ion, right? Next, if you have COOH here, correct? Instead of SO3H, if you have COOH, it is called anthranalic acid. It is called anthranalic acid. Okay. Next, if you have CH3 here, you call it as O-tolidine. If it is at ortho position, orthotolidine, or otherwise meta and paratolidine. Okay. All these reactions we have seen it already. What reaction we have not observed is this one, nitrous acid. See, if I take aniline, react with concentrated HNO3 and concentrated H2SO4. You will get ortho, meta, and para. Now, how come meta is coming? Usually, aniline is supposed to be ortho para directing, correct? So there should not be any meta product. But you could see there is a large quantity of meta product here. Now, why that is happening? The lone pair from nitrogen will take H plus, converts into anilinium ion. Thereafter, anilinium ion is a withdrawing group. Because it is withdrawing group, it will only have a meta directing nature. Benzene ring is deactivated, and on a deactivated ring, ortho and para are the worst positions to attack. So only attack can happen is on meta position. So from the meta position, it can extract NO2 and get this product. So usually this aniline converting into anilinium ion is close to around 47%. Clear? Right. Next. Aniline can also undergo sulfonation. That means when you treat with concentrated H2SO4, the lone pair from here will attack on H plus, converts into this anilinium sulfonate. And as soon as you heat it, this sulfonate will come out as SO3 as an electrophile, and from para position, the attack will take place, and you will get this as a Zwitter ion formation. So sulfonation is also happening on the para position, but only factor is first it will form like a salt, and then on heating, it will finally convert into an para substituted group. Okay. Friedel-Crafts reactions. See, aniline does not make any Friedel-Crafts reactions. Even if you have N-methyl aniline also does not make any Friedel-Crafts reactions. But if you have two R groups, then there is no hydrogen here, which can be removed out when a lone pair of nitrogen attacks. So that's why it, rather than acting like a base here, it could increase the orthopara activating nature and makes an attack from para position. That's how you can get it here. So only if you have NR2, you might be able to see some amount of Friedel-Crafts reaction happening. Clear, beta? Done? An issue here?
No.
Right? Okay. Now, as much as amines is concerned, these are the reactions which you have from the syllabus. Got it? So